Everybody, welcome to the last TFA Tech Forum for 2020. This week we've got Julian Hall, one of my colleagues in the ARM Trusted Firmware team, who is going to do an introduction about the Trusted Services project, which is a relatively new project. Without much further ado, Julian, please take it away.
Okay, thanks, Johnny. Yes, I'm going to talk today, just going through a few slides to introduce this new project. So my name is Julian Hall, as Johnny said. I work in the firmware group and in the Opti team. And this project really span out of some of the work we've been doing over the year. So the project is a new project under trustedfirmware.org, and it was first published very recently, just towards the end of November, and it originates from work we've been doing this year related to developing secure partitions, sort of services that will run in secure partitions that will provide basic security functions, and the focus has been on providing the sort of services that would be needed for PSA level 1 certification. And so the two services that we've been working on have been crypto service and the secure storage service. But a lot of what we've been working on has really been generic and can potentially be reused for really just about anything that you might want to run in a secure partition, or indeed in any other isolated execution environment. And so the project, I think, complements other trusted firmware projects quite well. I'll start drilling down into the details now. So just to give an overview of what we're calling a trusted service. And so it's a term that we kind of invented as a generalization for things we're probably all familiar with. And so it's a service that's performing security related operations on behalf of clients. And those clients might be running on a Linux context. They might be running as user processes. They might be running in containers. They could be running in kernel drivers, or indeed in a bootloader such as U-boot. And so we've got quite a diverse set of clients, and we're needing to provide sort of firmware-based services that are able to suit all of those. And we're in an environment where we have potentially multiple security domains and potentially it's a multi-tenant environment. So on Cortex-A devices, the sort of range of secure processing environments that are potentially available could be secure partitions, and there are different implementation options for those. The one we've been focusing on has been SCL0 secure partitions, where Opti is performing the role of secure partition manager. But equally, there are other options for performing this role, such as Hafnium or within EL3 firmware. And then, of course, there's the environment created by a T, such as Opti, where a service could be deployed as a trusted application. And there's also the possibility of the services being running on a secondary MCU within a secure enclave. And so I've mentioned the two services we've been working on, the crypto service and secure storage, but this is really a general model that could be applied to really just about anything that you wanted to deploy in one of these environments, such as a firmware TPM or maybe a UEFI key store. And there are probably many others that would fall into this category, into this general model, which I'll explain next. And so just to address the issue of why have a separate trusted services project, well, it's really the main reason is really about reuse, and to try and to avoid having to reinvent the wheel for implementing these sort of services for running in the different environments. So because there are quite a few opportunities for reuse, centralizing the components within a single project helps to standardize project structure, standardize the sort of layering, the way and the way we build and deploy the services in the different environments. So that's the real reason for consolidating these components and the deployment of the components as services within a single project. So importantly, it's, we were, as I say, we were working with Opti in its role as secure partition manager, but it became pretty clear that a lot of what we were developing were really independent of Opti, and so Opti was merely providing just one of many environments in which these services could run in. So the sort of opportunities that it creates would be adopting a common framework with standard conventions and solutions. So we start to ultimately standardize the way the clients access these services independent of where the services are running. So that's good for application writers, because it means that on ARM, independent of which protected execution, isolated execution environment is being used, the way they consume the service is potentially the same. And there's a lot of other work that goes into things like test cases, which can be reused, publishing and maintenance of standard interfaces, sharing of security enhancements, and having a common solution for how you build and test and export to different client projects. So all of these are really not that special for the different environments and can potentially be reused. So we set ourselves some project goals, which have really sort of strongly influenced the way we've approached things. And the number one goal, as I've already mentioned, was we wanted to make it easy to reuse components. So that meant that we need to be really careful about dependencies, careful about coupling between other components, so that it can be reused in a nice straightforward way, to be put together, to be assembled, to make different service integrations. And we also wanted to make it so that there was little baggage involved in consuming a service. So whether you're writing a kernel driver, or whether you're writing a user space application, or maybe something that's running in a container, whether you're writing in C, C++, or in Go or Rust, whatever, we wanted to make it so that it was easy to consume the interfaces provided by these services by different clients. And importantly, it means that we keep the dependencies on service interface definitions as clean as we can, to make it as straightforward as possible to use the services. Another important factor is coming up with a sort of generic layered model that allows for alternative implementations. So importantly, the way messaging might work, or the way this sort of remote procedure call mechanism might work, is going to be different for different deployments. But we wanted to be able to fit those within a standard model, so that you can slide in and slide out different layers without disturbing other layers. Again, making it, this is really something that's key to achieving the reuse goals. And as I've mentioned already, we needed to be able to support deployment of the different services into the different processing environments straightforwardly, and encouraging testing by making it really easy to add and run test cases. And one thing that we certainly set out from the start was to recognize that debugging software that runs in these sort of protected environments is sometimes quite difficult. And so where it was possible, we wanted to support testing and development in a native PC environment, to build that in as a requirement from the start. First of all, it makes it much easier to test a lot of the software, to develop it, to debug it, to enhance it. But it also creates environments for helping people writing clients that need to use these services to produce just PC-only versions of the services, that make it very easy from a development point of view to develop code that uses the services. We also wanted to make it very straightforward to reuse components from external projects without having to copy and maintain a fork of the project. And we wanted to, and importantly, we wanted to have a build system that would allow the trusted services project to integrate cleanly with customer projects such as Yocto or Build Routes, where trusted services are being built into an operating system. So the next slide gives an overview of the project structure on how we're trying to achieve those goals. And so the directory, the repo structure reflects the sort of the partitioning that I've illustrated on this slide. And I'll just briefly run through what each of these sort of categories actually mean that are useful. We're starting from the left. The protocols is just about exporting definitions of public interfaces to the services. And so this will be what operations a service provides, how you encode and decode parameters to it, and also protocols for some of the conventions that are used for status codes that are returned by operations. And so that's what the protocols are all about. And currently we're fairly flexible about what kind of encoding, what serialization is used for these protocols. We currently support 2, but we recognize that there are examples of where you may need to extend that. And so currently we have a sort of a fixed structure-based encoding, which is very similar to other interfaces to the firmware. And we also support a protocol buffers encoding as well. So that's what protocols is all about. So there's no code there. There's no, and this would be if you were writing a client, you would only be interested in creating a dependencies on the protocols part of the project. And our goal is to actually publish that as a separate repo. It's currently combined in a single project repo, but we can see that from a client acceptance point of view, it makes sense to have a separate repo so that you don't need to create dependencies on the rest of the project if you're writing a client. Okay, the components, this is really just where all of the code that we write lives, and these are separately reusable components that you can bolt together to create an integration that you can deploy in an environment. So components is just about sort of a repository of reusable components. So I use the word environment there. The environment represents the isolated execution environment that you might want to run these integrations in. And currently we support our secure partitions running under Opti. And we also support an environment which represents Linux user space running on ARM. And we also have another environment which is just Linux PC. And this is really just sort of a native Linux PC environment for building and testing within a Linux environment. But we can see the number of environments is definitely going to grow as we support new environments, execution environments. And the one in the middle, the deployments, is the thing that strings it all together. So for each, so a deployment is about taking a bundle of functionality, it could be a service or it could be a build for test purposes, and then deploying it to run in a particular environment. So a deployment identifies a set of components, a configuration, and a set of and an environment in which you want to deploy the build. And so we have deployments for the services, the ones I've mentioned before, the crypto service, the secure storage service, and we also have other deployments for test purposes and also for demonstration. Okay, tools is just about helping to build stuff. It's about common tools that we use to produce the builds. And external is about dependencies on external components from external projects. And what we generally do is that we have a if you like, a proxy for the external project that allows us to import it and configure it for the purposes of including it in a deployment build. So that's the overall structure. And then the other sort of structural element that I'll introduce is the common layered model, which sort of generalizes the view of what one of these trusted services looks like. And so we've adopted a very simple layered model, and I've illustrated it here with a sort of fairly typical layer cake diagram, which shows the peer-to-peer relationships between the client and the service provider. And so the three layers we're dealing with, one is the sort of the service specific layer, which is the blue one at the top. And that, so for example, is about talking a particular service specific protocol, which is about particular operations and a particular set of input and output parameters for each of those operations. And that's built on an RPC layer. So we view a trusted services as always being able to fit this RPC model, a remote procedure call model, where a service provider implements a set of operations, and an RPC layer allows you to invoke those operations, passing a serialized set of parameters and returning a serialized set of response parameters. And then beneath that, we assume that there's a reliable messaging layer. And for a service provider to do something useful, there's nearly always some kind of dependency on hardware, or dependency maybe on other trusted services. So for example, it might be a dependency on some flash storage driver. It might be a dependency on some crypto hardware, or it might actually be a dependency on an external secure enclave. We're kind of flexible about what those back-end dependencies are. But that's the sort of generic common layered model that we've adopted, and it's very strongly represented in the component source tree. And so where we can, we standardize the upper edge interfaces of these layers to allow for alternative implementations, allowing the higher layer, for example, the blue service layer, to be agnostic about how you're actually achieving the RPC mechanism. Okay, so the next, I'm just going to talk a little bit more about protocols. So as I mentioned before, these are the public interface definitions for each of the services. And what a service access protocol defines is the set of operations. And so, for example, for the crypto service, that would be things like generate key, encrypt hash, verify hash, these sort of distinct crypto operations. And they also define the per operation input and output parameters, and also any service specific status code that codes that get returned. And we also allow for RPC protocol definitions if you need to build your own RPC layer that runs over some sort of reliable messaging layer. And we've done exactly that to allow for messaging over FFA to deal with the communications between normal world and secure world, or between different secure partitions. And there we've defined some conventions for passing RPC parameters via the FFA direct calls, and then returning the responses via the return parameters, and also a convention for how we serialize the input parameters and how we return the output parameters. So as I said earlier, we're planning to keep the protocol definitions in a separate repo to make it really as simple as possible for external projects to consume those definitions without taking on the baggage of creating dependencies on the rest of the trusted services project. And so the project structure under the protocol definitions allows for alternative definition mechanisms, different serialization mechanisms. So because it's difficult to second guess what actually will be needed, because you can see that for different types of services there may be existing conventions on how parameters are passed, and to accommodate that we've built that into the structure. And at the moment, as I said, we've got 2 serializations we support. The protocol buffers is based on Google protocol buffers, and that's particularly convenient for non-C, C++ clients, because there's a formal interface description in a language agnostic interface description language, which allows different clients to be different client interfaces to be generated using standard tools for your chosen implementation language. And we also have what we call PAC-C, which is very similar to the SCMI interface that's used elsewhere in trusted firmware. And it extends that to support variable length parameters. And that's going to be good for C clients. For example, if you're writing a kernel driver, it would make good sense to use the PAC-C encoding rather than the protocol buffers encoding. Okay, so that's protocols. Another interesting area where there's strong reason to standardize is this idea of client identity. So we're running in these secure execution environments which are hardware backed and provide good isolation. But equally important is ensuring that you're able to implement strong access control at the service interface. And one thing that's pretty fundamental to any kind of access control scheme is having some kind of trustable notion of the identity of the client that might be making a request. So however you implement your access control policy, you need to be able to have some way of being able to trust that you know who is making the request. And so we're building on the components that we have in the call path to allow us to start adding some secure notion of, or trusted notion of, client identity, and that can be the perspective of identity on a requesting client can be different. You have a different perspective on that depending on which layer you're running and which execution level you're running at. So, for example, a kernel driver could add the user ID could provide a fairly trusted view of the user ID or the SE Linux label for a calling process. And so we made provisions for that to be inserted by a kernel driver into a call request. And similarly, when we're running over in the secure world and we're running over FFA, there's the opportunity for the secure world side of things to insert the source partition ID in a request. And so there you can see those in combination give a fairly useful trusted view of the calling client, and are quite difficult for to be forged by a different client. And that can then be built on, used as a building block for implementing access control at the service interface. So that's an area that is a pretty generic problem across all the different services, classes of service, which we're hoping that people will be able to build on to implement service-specific access control as needed. Okay, this just gives a kind of sort of status of the current deployments that we support at the moment. This is something that's going to grow and grow, I think. But just to give you an idea of the current status, we've got 2 deployments related to services. There's the crypto services running within a secure partition under Opti, and the secure storage service also running under Opti within a secure partition. And we have other deployments that are concerned with test, which we've got one called component test, which is really just a bundle of components and corresponding test cases that can be run within just a native Linux PC environment or on an ARM environment, so running standalone tests. We also have end-to-end service tests, and this is what the TS service test deployment on Linux PC or ARM Linux is about. And so that's about either testing the services end-to-end against a PC build of the bundle of services, or when you're running on a Linux platform, of real deployments of the services running in some kind of secure environment. We've also got a demo program, and we've got a library that can be built called libts, which helps with client applications. If you want to, it gives a generic solution for locating a service and for opening an RPC session to the service. You don't need to use that, but it does give, that does mean you can reuse that. And we certainly use libts for our service level testing. And there's also a library that we developed at the secure partition end, which provides a standard interface for accessing the low-level FFA primitives. Okay. And all of those are built by the project build machinery that we've developed. I'll just give an overview on some of the build conventions we've adopted. So all of the deployments are built. The builds are based on CMake with CMake configurations. And the unit of reuse for a build of source code is a component. As I mentioned before, we have the components top level directory, and groups of source files are grouped together within components, each one defined by a separate component.cmake file. And so this makes it really quite easy to put together different integrations by just collecting a relatively small number of components together. And so this gives us good maintainability properties. And so where components are modified, and we might have multiple deployments depending on those, only the components makefile needs to be changed without actually having to change the deployment makefile, the deployment integrations. So as I said, all of the deployments live under the deployment's top level directory. And a concrete deployment is defined by a combination of a descriptive name, such as crypto, and an environment. And that combination of the two is reflected in the directory structure. So at the bottom here, I've illustrated a deployment, which is the TS service test. So this is the one that was about running service level end-to-end tests. And you can see there that it's deployed in ARM Linux and in Linux PC, native PC environments. And there's also commonality between the two, and those are captured in a parent. So we support a sort of specialization type structure that's reflected in the directory structure. Okay, that's build conventions. And now test. So as I said in the project objectives, building test into the way we do things right from the start was really quite an important objective, and making it really easy to add tests and run tests was important, and we certainly benefited from that quite strongly during the development. So we're using CPP test for which is just an open source test framework for running the C++ based test cases. And we don't treat test components exactly the same as any other components. They're just source components that you can assemble together to produce an integration that can be deployed in a particular environment to run tests. So we found that not treating the test components as anything special actually gives us a whole lot of flexibility. It means you can use exactly the same deployment mechanism to piece together a build for, and the role of that is to have a combination of components under test and test components, and to deploy them in an appropriate environment. So an example of that is, and where we put the test components, they're freely scattered around the components source tree at points in the tree that reflect the scope of the tests. So again, that gives us a nice flexible structure to allow us to have very small unit level tests, maybe subsystem tests, or maybe sort of service level tests, and the scope of the test cases are reflected by where we put the test components in the source tree. And we've adopted the convention of putting test components in a subdirectory called test. And I've given the example there of some service level tests for the crypto service. So there are currently 2 test related deployments. One, which is just about component level tests, which will just grow and grow as we add more tests. And that normally gets run simply on the developer's PC. But it can also be run in a cross-compiled and run on a target ARM platform. And the service test deployment, which is about end-to-end service tests. So adding new tests, there's a very, very low barrier to doing that. You just freely add new tests to existing test suites, or add new test components simply by adding these. And really, the more the merrier on that. Okay, so that's testing. And so just a few more words on supporting development in a native PC environment. So I think before I worked on this project, I hadn't really done too much developing the sort of the service side code that runs in these execution environments. But I understand from colleagues that it can be something of a black art. And so, by definition, running, for example, under Opti as a trusted application or in a secure partition, it can be quite tricky. It's deliberately difficult to get visibility about what's going on. And so to really to try and make it easier to test and debug code, we made it very straightforward to run components within a PC environment. So you can just use much more conventional approaches to test and debug. And so as a rule, if a component can be built and run in a native PC environment, it should be. And the way that something that's made that
into the Maya, and we're going to use that as a transport for JSON RPC based configuration of.
It could be. It could. I mean, to support an RPC level, an encoding using JSON RPC. Yeah, I mean that would we don't support that at the moment as an RPC, but it would absolutely fit the layered model. So, for example, a way that you would achieve that would be to add a new RPC implementation that used JSON RPC. And either use one of our existing encodings protocols or add a new encoding if you needed to. But then the service clients and the service provider can work quite happily in that environment. What we do have to support this, we currently have a direct RPC caller, which really just calls directly into. So everything for testing, everything is just built into a single monolithic build, and then the direct RPC caller just calls directly into the service provider. But a JSON RPC that did something equivalent to that would work just fine. So yeah, that's exactly the sort of thing we want to allow people to do. Okay. That's probably, I've probably covered just about everything. So I put a few links here to where the project is, and I put my name and other people on the project too if you've got any other questions. But yeah, if anybody's got any other questions, yeah, I'll be happy to take those.
Hey, Varun Wadikar here. I have a question on the cake diagram that you had shown earlier in the slides.
Yeah, let me see if I can get back to that. Yeah, that one.
Right. So I was just wondering if you could map these these blocks to the actual software components that that implement these, just to give us an idea. I mean, you talked about, the clients and then how they would work on top of Opti or Hafnium or EL3 based
Yes.
SPM
Yeah.
components. So
Let me give some. I'll give some examples of ones we've implemented and see and explain how things are partitioned. So what we're currently running under Opti within secure partitions, and we're using FFA for messaging. And so the bottom layer, the sort of the green layer, is really dealt with by FFA in the so far, and that uses FFA direct messaging and memory management to allow us to pass RPC parameters within a message. And so we've pieced together, we're using these sort of register-based FFA direct messages and the memory allocation to allow a higher layer, an RPC caller, to pass an arbitrarily sized message to the corresponding layer, and then to return the response parameters. And so the RPC layer in this case is responsible for so at its upper edge, it presents a pretty conventional RPC model. And so that's really about invoking an operation and taking a serialized string of parameters as the input parameters and returning the response parameters. And that uses, in this case, the FFA messaging to call methods and then to return responses. And so in this layered model, the serialization of the parameters lives in the blue layer. And so, for example, a client, if I go through the steps that a client would need to perform to invoke a method. So let's assume that an RPC session has been established. And so that means that there's you've discovered a session, a service provider, and you've created, you've got state, you've created state at the client side, which creates an association between the an RPC caller and a particular service instance. Then, having reached that point, then the client is able to invoke operations by qualifying the operation they want with an opcode ID, which is just an integer, and passing a serialized stream of bytes, which represents the parameters in the encoding that the client wants to use. And so that will be serialized, for example, using the protobuf serialization, or using out this fixed C structure serialization, or indeed any other serialization that needs to be used. So that's the separation between between the layers. And then at the service provider end, it's really the opposite of that. And so the FFA messaging gets us to a particular FFA endpoint, which would be a secure partition. And then the RPC handling there understands how to take those parameters that were passed via FFA and then present them to a service provider as an endpoint for an RPC call. We have this idea of a generalized view of an RPC interface, which is just an interface that takes a set of call parameters, a call request that's handled by the service provider. So you can see there the service provider would sit quite happily over any RPC endpoint implementation that was able to present the incoming request via this standard RPC interface. Don't know if that makes it clearer.
yeah, it does. Thanks a lot.
Okay.
And if I may ask another one, on the client identity slide, I was just curious to understand if you were also able to tackle a situation where you had to. I mean, any client can masquerade as another client. So, is that something that you aim to solve?
Well, sorry, that's the wrong one. The way that it's the way that it's solved is by exploiting that it's not the calling client's responsibility to identify themselves. So let's say that it's a user space process running in EL0. It's the responsibility of higher privilege level components that are in the call path to identify the client that initiated that was earlier in the call path. And so I think in the in the fourth bullet point, I've given an example of a call path. And so and here there's there's a calling process. Let's say it's a Linux process that's running at EL0. And so the kernel driver that's dealing with that would be responsible for identifying the process UID or SE Linux or some label that identifies the process. And so the idea would be that based on the integrity of the kernel, it shouldn't be possible for a different a calling process that's running under a different user ID to masquerade as another user ID. So that relies on the integrity of the kernel for the user ID, and then there's a similar labeling that goes on as the call traverses through to a higher privilege level, where the secure part, the secure world has this is in the context of FFA, has an idea of the partition that the call came from, and so there it is able to insert into the call request the partition ID of the caller. And again, it shouldn't be possible for a call from a different partition to masquerade as a call from an alternative partition. So that's the way I think that we're building up this robust notion of client identity.
Hey, sorry, I joined in late, so forgive me if the question is stupid, but it sounds like the secure world is depending on the normal world to make sure that there is no messing up of the client identity, right? If the kernel is malicious, then the service provider has no robust notion of client identity. Is that?
Well, it's certainly true that it gets we're progressively relying on we're relying partially on we're relying on higher privilege levels, whether those are higher normal world privilege levels or the secure world view. But we're building up that notion of identity. But you know, so for example, if a compromised kernel, with a compromised kernel, it would be possible to masquerade as a different user ID, but we still have the fallback of the partition ID being non-masqueradable. And so the idea would be that it's the notion of identity would be rely on a combination of all of the identities that have been built up over the call path.
Oh, how does secure monitor at EL3 know if a client ID given by a malicious kernel is correct or not?
I'm not. It's in FFA. This is one of the FFA goals to achieve this. I'm not sure how that's achieved. I'll need to get. I'll look into that and try and let you know how that's done.
Let me just
I'll
help out there. So it's the fundamental concept here is that wherever you have a malicious actor, of course, the client identity information up to that point is, of course, non-reliable. But for example, the SPMC component has an understanding of all of the secure partition identities, and the SPMC is part of the root of trust in the system. So for example, no matter the extent of corruption on the normal world execution, no normal world client can ever act as a secure partition, because the SPMC has that information and can validate that the call comes from the source that it is alleged to come from. So we cannot distinguish between normal world components in that case, but we can distinguish between secure and non-secure components. The same goes, for example, take the example when the hypervisor in the normal world is not malicious. In that case, we can identify the virtual machines because we can trust the hypervisor to be able to distinguish between virtual machines. So even if the kernel within one of the virtual machines gets hacked, in that case, we cannot, of course, tell apart client identities within that virtual machine, but so long as we can trust the hypervisor, we can trust that it will validate the partition ID for the FFA message. So
all right, so I understand. Sorry, finish your thought.
Yeah, I just wanted to wrap up. So it's always a layered approach to protection, and of course we cannot, from the secure world, verify the identity. We have to delegate some of that responsibility to the normal world, but we can compartmentalize and contain the propagation of errors to within the various trust domains in the system.
Oh, but isn't that a broken model? So I understand what you said, right? So from, especially between secure and normal world, right? From a secure world point of view, anything that comes from normal world should and must be treated as untrusted, right? So at the service provider, you should not be, you should not think of a client identity as trusted, right? And the service provider should not consider any identity that is provided by the normal world as robust, and you should not depend on it either. All the services should assume that it has no notion of client identity, or if it is spoofed, it does not cause a security issue.
I think it's not black and white, and it's because, remember, we like to be running on multi-tenant systems where we have different security domains running within the normal world, and so it isn't as simple as just partitioning between secure world and normal world. There'll be, I've come across many applications of where there's a requirement to partition the secure world, for example, key store between different normal world security domains, and that by definition needs to be reflected by a normal world identity. And so whether how this identity, this complete identity that's built up based on normal world and secure world IDs is used is based on the access control policy. But if what's needed for a particular asset is a partitioning between normal world security domains, that by definition has to rely on a normal world identity. So it's down to, we're putting in the building blocks here to allow arbitrary access control policies to be adopted. And if people want partitioning by normal world security domains, that has to be based on normal world identities.
Hello. If I may add to what Miklos said. So what we are trying to do is provide a unique identity for a client and prevent one client masquerading as another client. That's the threat we are basically trying to avoid here. So as Miklos said, if you have one of your virtual machines compromised, what we are trying to ensure is any client within that virtual machine cannot masquerade as a client in another virtual machine. But it is possible for the client within the compromised virtual machine to masquerade as a client within the same virtual machine. Do you see what we're trying to get at here? So if we say that the Linux kernel of one of the virtual machines is compromised, all the EL0 clients within that virtual machine would, it's unreliable, the client ID is unreliable, but as long as the hypervisor is secure, is not compromised, another virtual machine which is running under the hypervisor and a client under that is still able to prove its identity. The original compromised virtual machine and the clients under that will never be able to masquerade as a client in a non-compromised virtual machine.
Right, I understand that. I guess the problem is extending secure world trust to a hypervisor, right? So if you are saying the hypervisor is secure, why would you even put a service in secure world? Why not just run it as another VM, right?
Yes, so that comes down to if the hypervisor is compromised, it doesn't need to even spoof the client ID because it can do anything really. So there is the trust breaks down over there because if we say that we have a compromised hypervisor, then any of the virtual machines running underneath is compromised even without the client ID being reliable. So yeah, we are building this layer of trust, and as long as the highest component or the higher component is trustworthy, an independent component underneath it is still isolated from a compromised component underneath it, if that makes sense.
Yeah, that makes sense. So I think I was trying to understand what you meant by robust identifier. So it sounds like robust identifier is the robustness is dependent on, at least for normal world clients, is dependent on the highest privilege level code being secure.
Yeah.
If that breaks down, then
Yeah.
your service essentially cannot make those guarantees.
Yeah.
At least from usually the way I have seen this is, generally services don't rely on anything from the normal world, right? So we have no notion of robust identifier from the normal world. But okay, I understand. Thank you.
Okay, I think we're nearly out of time, actually. I wasn't expecting to use the whole hour, but yeah, we have. So if anybody has any more questions, we've got a couple of minutes.
Hey, Varun Wadekar here again. Just wanted to understand the direction of the project. I believe at the start you said that this is not really tied to Cortex-A machine. So, for example, anybody can run this on a TFM as well. Is that
yeah? I mean, the focus has been on supporting the different environments that are likely to be on Cortex-A. But there's really nothing that we've done, and that includes running service providers on a secondary MCU on a secure enclave. There's nothing that we've done that actually restricts this to Cortex-A as the focus, but that's certainly what the project has been about. So I don't know where it's going with respect to, it's certainly, where our focus remains on extending the services that we're making available, dealing with different ways of storage, dealing with different ways of storing, providing persistent storage. So it is definitely Cortex-A focused, but there's nothing that we've done in the structure to restrict things to that. And it would certainly make sense to be able to consolidate our service implementations, where possible, wherever they're deployed, because a lot of what we talked about are generic problems independent of whether they're running on an M class or an A class. But yeah, the direction of travel where we are at the moment is everything is focused on A class, but with the possibility of running service providers on M class secondary MCUs.
Yeah, thanks. Makes sense.
Okay. Okay, right. Well, thanks for listening. Thanks for all the good questions.
Okay. Okay. If there's no, I think we have run out of time. It's about a minute to go. So thank you, Julian, for your presentation. I'll endeavour to get the recording and the your slides uploaded to the trustedfirma.a Tech Forum page before Christmas, if I can. The next TFA Tech Forum, I think, is scheduled now for the 14th of January. I don't have a subject yet, but I will work on one in the new year. If any of you folks have an idea or have something that you would like to present in early January, 14th is the deadline, please reach out to me. Otherwise, I will find something from our backlog of work and subjects that we would like to talk about. Without much more, really, I'm going to sort of end the recording, and which I have just done.